Um, we also need to look at transformations of exponential graphs, and we're talking about dilations. And if we remember from when we were looking at quadratic graphs and we had y equals x squared being the base quadratic graphs, and we had a look at a situation where we had y equals a outside of x minus b all squared plus c. And if you recall, this A controlled the dilation, and if A was greater than 1, then the graph became very narrow, and if A was less than 1, but obviously still greater than 0, then it became very wide, and obviously if A was less than 0, it was flipped upside down. We also had a look at the B, which controlled the left and right translation, or the movement of the graph left and right. And if we had a situation where we had x minus 3 all squared, that moved it 3 units to the right. But if we had a situation where we had x plus 3 all squared, that moved it 3 units to the left. And you might recall that the plus C on the end moved the graph up and down, up if it was positive and down if it was negative. These same transformations, so dilations and translations, also occur with exponential graphs, and that's what we'll be looking at in this video. So the first thing we want to look at for exponential graph is reflections. And we're going to look at two situations. That's where we have y is minus a to the power of x. And also we're going to look at where we have y is equal to a to the minus x. And we'll see what sort of reflections we get with both of these situations. So here we have our base graph, and if I was asked to guess what this was, we can see that it goes through the point x equals 1, y equals 2. So this is most likely the graph of y equals 2 to the power of x. We can't be sure unless we see a few other bits and pieces, but this would be the most likely guess. And if I open up my little graph here, you'll see that I've got y equals a to the x and a is 2. So this is y equals 2 to the power of x. Let's see what happens if we have negative 2 rather than 2. So let's just turn this graph on. And here we have the graph of y equals a to the minus x. It is a reflection in the y-axis. So every point here is a mirror image across to the other side of the y-axis, and this green line is being reflected in the y-axis, and this is the graph of y equals a to the minus x. Let's just moving this up the graph a little bit here. Let's see what happens when we have y equals minus a to the x. And like we saw from our quadratics, when we have y equals x squared is a normal parabola, y equal to minus x squared is an upside down parabola, we'll see the same thing here, that if this blue line is y equals a to the x, then this red line is y equals minus a to the x, and it's been reflected across the x-axis. So looking at these two situations, a to the negative x reflects in the y-axis, y equals minus a to the x reflects across the x-axis. And the way to remember this is that we've seen many of these y equals minus a to the x, so we've seen many y equals minus x squareds or minus x cubes where it flips the graph upside down across this x-axis. Same here, and this extra one, y equals a to the minus x, has been thrown in for good measure. Now we're going to have a look at translations, and just like we had with our parabolas, y equals x minus b squared plus c, where this value inside the bracket with the x controlled left and right, and the value on the end controlled up and down. Very similar thing happens here with exponential graphs, and we're going to look at two situations, one where we have y equals a to the power of x minus b, and y equals a to the x plus c on the end. Now, I should just warn you here is that I'm going to show you x minus b inside the brackets here, but many books show you, and our book as well shows you a situation where you have y equals to the power of x plus b. And that becomes very, very confusing. But if you think just a little bit carefully about what happens here, the movement is the same way. So if you have y equals 2 to the power of x minus 3, that is going to move the graph 3 units to the right, regardless of whether it's written or whether you've seen the rule written as x minus b or x plus b. If it's a minus 3, that moves it to the right. If you have y equals 2 to the power of x plus 3, then that's going to move it 3 units to the left. So I prefer the use of x minus b because it fits with everything that we've seen so far, especially when we've been dealing with the parabolas and quadratics and so on. So once again, we're going to start with our graph of y equals 2 to the x. This does look like y equals 2 to the x, which it is. Let's have a look. Our green line here, because b is 0, it's exactly the same. And as I increase b using the x minus b, if I make b positive, that should move this graph to the right, which is, you'll see that it's moving to the right. It doesn't look quite the same as our quadratics, where it always looked exactly the same. The shape of this particular exponent is not changing, but visually it does look as though it's sort of laying flatter along the x-axis, but it's just moving it left and right. And I'll show you what I meant before with the parabolas. So here I have down here, this other green line here is the graph of y equals x minus b all squared. And you'll notice that as I move the b, both graphs move the same way. Don't try to think of is b positive, is b negative, whatever, what is the value of b. Just have a look in the graph. If you end up with x minus 5, we know it's moved 5 units to the right. If it's x plus 4, we know it's moved x units, 4 units to the left. Let's set this back to 0. And then also the c on the end, as we would expect. Let's have a look at this red line here, which is y equals 2 to the x. This c moves the graph up and down. Again, it looks as though it's changing the shape, but it's not changing the shape. It is literally translating the unit up and down. We'll see here that this point here has been translated 1 unit down. This point here has been translated 1 unit down. This point here has also been translated 1 unit down. It's just an optical illusion to think that the shape of the graph has changed. And lastly, we'd like to look at dilations. And if you remember from quadratics, that's where it made the graph either very narrow or very wide. Similar thing here. There's 2 types of dilations that we want to look at. We're going to have y equals some constant out the front of, or some constant multiplied by a to the power of x. And we also need to look at y equals a to the kx, and that's a new value here, this k, where we multiply the x or the power of the x up here. So let's have a look at these now. Once again, let's start off with just our base exponential graph. Once this does look like y equals 2 to the power of x, because it goes through the point x equals 1 and y equals 2. Without knowing the transformations, we don't know that exactly, but if it is a non-transformed graph, then it's definitely y equals 2 to the power of x. And if we have a look here, we got y equals a to the x, and our little a here is 2, so that's what's happening. So let's have a look at our first dilation, which is where we multiply the graph by a constant out the front. The constant is currently 1, so this is now our green line. As we increase this constant, you'll see that the graph changes shape, and it is in fact getting steeper and steeper and steeper. It's very hard sometimes to distinguish this between
just translating the graph, moving it left and right or up and down, or dilating the graph, which is making it steeper or shallower. But if we take a look here, we can get a hint. So this point here has been moved up the y-axis 1 unit, but this point here has been moved up the y-axis 2 units. So it's not a constant move, it's not a constant shift, therefore it's definitely a dilation as along the y-axis. So as A gets higher and higher, the graph gets steeper and steeper and steeper. As A gets below 1 and it becomes a fractional value, it looks as though this graph is getting a lot shallower. It's laying out along, it's sort of laying down along the x-axis. This is still a dilation along the y-axis, or away from or towards the x-axis, but it's called a dilation along the y-axis. Obviously, if A gets to 0, the graph gets flat because 0 times everything is 0. And then if A is negative, it flips the graph upside down, as we've seen before. And if we look at this in relation to our quadratics, here we have y equals a to the x squared. You'll see a similar thing as a gets larger. The parabolas here get narrower, so does our exponential graph. And if a is a fractional value, then it gets shallower or wider. And it's a very similar effect as the quadratic graphs.
Now let's have a look at the other dilation that we talked about, y equals a to the kx, where k is a constant in front of the x. This is a dilation along the x-axis, and we're going to see what this means by looking at two situations here. So let's have a look at the graph of y equals 2 to the power of x and y equals 2 to the power of 3x. Now, we've looked at this before. I've already filled in the values. When x is minus 3, y will be 1/8, a quarter, a half, and so on, up to 2 to the power of 3. Remember, this is 2 to the power of 3, which is 8. Now, let's have a look at when we have y equals 2 to the power of 3x. When x is minus 3, 3x is minus 9, so this becomes 2 to the power of minus 9. Not 2 to the power of minus 3 as it was over here, so 2 to the power of minus 9, which is 1 on 2 to the power of 9, which is a very, very small number. And this here becomes 2 to the power of minus 6, and this becomes 2 to the power of minus 3, which is 1/8. Anything to the power of 0 is 1. And again, this becomes 2 to the power of 3, which is 8. This becomes 2 to the power of 6, which is, of course, 64. And this becomes 2 to the power of 9, which is really, really big. And what we've seen here is that the effect of this constant in front of the x is, and in this case, the constant is a positive value, it magnifies each of these points, or in fact, these points become a whole lot smaller. So any point that was small or below 1, any fractional point becomes a much larger fraction, so much smaller overall. And these here become magnified. So instead of 1, 2, 4, 8, we get 1, 8, 64, and something really, really big. And we'll see how that works in a minute.
So this purple line here is y equals a to the kx, and k is currently 1. Let's change k to 3 like we had a minute ago, close enough, and you'll see the effect that I was talking about. All of these values which are fractions, which are less than 1, get a whole lot smaller. The graph still goes through the point 0, 1. That's because regardless of what k is, if x is 0, this becomes a to the power of 0, which is 1. And then these points over here get much, much larger. It sort of looks as though it's rotating it around the point here of 0, 1, and it's changing the value, or it's magnifying the value of x, if you like. And this is called a dilation along the x-axis. If k becomes fractional, or k becomes less than 1, between 0 and 1, the opposite occurs. These fractional values here get increased, but these these values larger than 1 here become decreased, and so the graph lays flat a little bit. If k becomes negative, we'll see an inverse effect, and if we get k equals to -1, we'll see very similar to what we had before, where we have y equals a to the minus x, which is a reflection across the y-axis. So this is the effect of k. It sort of rotates it around there, if you like, but it makes the graph, it magnifies all the values away from 1, if you like. So this value here, if k is positive, gets further away from that point 1, and each of these values here get further away from this line here, x equals to 1.
So there we have our transformations of exponential graphs, graphs of the form y equals a to the power of x. In these graphs, I've shown you mostly y equals 2 to the power of x, but the same things happen regardless of what the base is, and so that's why we talk about y equals a to the power of x. Whenever you're asked to draw a question with graphs, with exponential graphs, there's two main points that they're going to want you to look at. So if we have a graph like this, obviously that's the x and the y. They're going to want to know the y-intercept. And obviously that always occurs at x equals 0. They're also going to want to know what happens at x equals 1. And if it's just a basic graph like y equals 3 to the x, then obviously when x equals 1, y will equal 3, or y will equal the base. But when there's transformations, obviously this number will change here. And if we have a standard graph like this, there won't often be an x-intercept, but wherever we have a plus c on the end, and that ends up being a negative, so wherever we shift that graph down, we may end up with an x-intercept, and so obviously you'll need to find the coordinates of the x-intercepts as well. But if there are no intercepts, quite often the x-axis is the asymptote. It approaches and approaches but never quite touches. If there's no x-intercepts, you can't find it. Just look for the point, the y-intercept, and the point at x equal to 1.